Hello and welcome back to the second lecture of Chapter 1, Introduction to Cognitive Psychology. We finished up last time talking about the rise of behaviorism, and we talked a little bit about how the shift from psychology as a purely philosophical concept moved into Donder's and Ebbinghaus's labs, the first establishment of the first psychology lab by Wundt in Leipzig, and this idea of using empirical methods to study behavior, how that moved from a purely mindful experience, so the examples of analytic introspection along with reaction times were used, and then from the perspective of some psychologists, like Watson and Skinner, this was seen as too subjective and too reliant on the individual's experience, which then yielded this result of the rise of behaviorism. And if you can see on this timeline, that progression put us in this place around 1938 as psychologists where we were questioning, or at least a lot of American psychologists who were relying more on behaviorism to study observable behavior. There was a question of what is the mind and what is free will, and how do we actually experience the world outside of just the observable behaviors that we make. So that's just kind of a really quick, in a nutshell, in the last lecture. Before I get started, I wanted to apologize for being so late with this lecture and the quizzes. I've been a little sick, cue coughing, and so I've just been trying to get a little bit more well, and so taking some Dayquil this morning and giving myself a little bit of extra rest has been helpful. Thank you for your patience and understanding. A few notes on the chapter notes. Everyone's done a really stellar job, especially considering that some of you didn't have the same book that was required and had to use the older PDF that I provided. Make sure if you don't have the book, you need to get the book in order to accomplish these chapter notes. Specifically for the key terms section, I'm giving a little bit of leeway for this first assignment because it's the first time that we've done it. But I just wanted to make sure to reiterate that there is a list of key terms, and those bolded terms inside the text. You're responsible to list and define all of those terms to receive full credit for that question. Feedback is great. I've really appreciated all the feedback on the videos as well as how the chapter notes are situated. So if you have questions or concerns or anything like that, please feel free to provide those. I'll be grading them this weekend. Make sure to always provide something on the confusing or interesting section. This is a really helpful tool for me in order to emphasize or reiterate concepts that might be a little bit more confusing when I do the second lecture. And then make sure to turn it in on time. I'm going to allow those of you who haven't been able to turn in the chapter notes to turn them in by midnight tonight. And the chapter quiz, I'm shifting that due date to Tuesday, this coming Tuesday. So you'll be responsible for turning in your chapter notes for for chapter 2, as well as completing quiz 1. So if you have any questions, please feel free to email me even before this video goes out, I guess. But you'll be seeing this right now, so you'll be emailing it. Anyways, into the second half of the lecture. Now, with this big focus on behaviorism and this idea of only studying observable behavior, you had a small shift within American psychologists. So this example is specifically Tolman in 1938, asking questions about things more complicated than operant and classical conditioning. Thinking about how, in this case specifically, rats find food and remember where food was presented to them. So what Tolman did is he came up with an experiment using a maze, rats, and food. And he hypothesized that there are these two competing interpretations. One interpretation is the behaviorist perspective, which predicts that if a rat finds food when it turns right, that behavior of turning right will be reinforced. And so there's a greater likelihood that that rat is going to turn right because it's basically learned behaviorally to turn right. Well, Tolman had a competing hypothesis with this, is that rather than just rats learning to turn right, that these rats were actually creating representations of the mazes they were running in their brains, albeit very simplistic ones, but that because these rats were making cognitive maps, they weren't just learning to turn right, they were actually learning the location of the food and how to best navigate the maze. So it wasn't just this more simple stimulus response system. There was actually some sort of cognition going on, in this case, mental mapping of a physical space. So the question became, what happens when the rats are placed in different arms of the maze? Now, for BF's Skinner's perspective, what he would say is that since the rat learned to turn right, it's always going to turn right. So in this example, if I put the rat at A and I put the food at B, the rat, and I do that enough time, the rat is going to learn that I need to turn right to find food. So if I then put the rat at C, rather than what's represented in this graphic, the rat is going to turn right as opposed to left. It's not going to go directly to the food. And exploration of the maze doesn't really matter because there are no reinforcers that are making this idea of the maze persistent for the rat. Now, what Tolman would say is that because the rat is exploring the maze, it creates this mental map of where the food is. This allows the rat to basically perspective take. Think about how when you're sitting across the table from someone and you try to mirror their actions. If you raise your right hand, they raise their left hand. If you say raise your left hand, they're going to raise the opposite hand of you. This idea of being able to perspective take regardless of your orientation is something that is much more cognitive than just a stimulus response system. Now, what do you think happened? Well, when the rats were placed in different parts of the maze, they were still able to find the food, essentially demonstrating that the rat had created this mental map of where the food is and was able to navigate to the food regardless of where it was placed in the maze. And this provides some insight into this black box that's happening and kind of flies in the face of this perspective that the rats were just using stimulus response to learn to always turn right. And did not support the behaviorist perspective. Now, this is one of the first experiments done in American psychology regarding kind of challenging this behaviorist perspective. But throughout the rise of behaviorism, there were always questions regarding these higher cognitive abilities that humans have and whether or not we are just stimulus response machines. And one of the biggest arguments that psychologists had was about language acquisition. And now one of the reasons for this argument is that in a book that Skinner published even later than Tolman's experiments using rats, Skinner espoused this idea that children learn language through mimicry. And that basically they imitate the speech that they hear, and if they speak correctly, they're rewarded, therefore reinforcing the behavior. If they speak incorrectly, they're punished or not rewarded, therefore decreasing the likelihood that the behavior would happen again. And for a lot of psychologists and linguists and cognitive scientists in general, this was not an acceptable hypothesis regarding language acquisition. Now, because of this publication, there was this guy named Noam Chomsky, who is a cognitive scientist and linguist, who argued that children don't just learn language through imitation and reinforcement. They can say things that they've never heard before. So that doesn't explain that spontaneous generation of language. And they might say things that are incorrect, and they haven't been rewarded for saying those things. So the reinforcement of that behavior isn't working, or the punishment of that behavior isn't working. And what Chomsky theorized is that language was determined by an inborn biological program, and not so simple as a biological program like a computer, but the idea that we contain a grammar in our head. Essentially, we're wired to learn language, and as we experience different languages when we're younger and we use those languages, we develop an ability to speak and understand other people. Now, in order to understand these complex cognitive behaviors, the problem that Chomsky and other linguists and people trying to study these more complex behavioral patterns, they had to measure observable behavior. So in a similar way to behaviorists and similar way to early cognitive psychologists, they had to be able to isolate observable behaviors. They had to make inferences about underlying cognitive activity. So the example of the rats in the maze, making inferences about how the rats navigated the maze, because they were demonstrating behaviors that can't just be explained through stimulus response models. And then to consider what the behavior says about how the mind works. So going into that kind of hidden area of those observable behaviors and make hypotheses and then test those hypotheses in order to determine what sort of cognitions we're using. Now, because of this shift and because of this, the complications brought on by a lot of these higher order behaviors that behaviorists couldn't explain, at least not satisfactorily, there was a shift from the stimulus response relationship model to understanding the mind again, but in terms of behavior. So trying to situate the mind in a behavioral space. And this prompted scientists to take an information processing approach. And this is an idea that by that time we developed computers. And so looking at how computers work and how we can program computers to accomplish things that oftentimes we can put an input in, get an output, and I might be a complete layman and not know how that computer is designed. To me, I just see an input and I see an output. And so this cognitive information processing approach focused on understanding the computer itself. And in order to do that, you had a lot of cognitive scientists becoming computer programmers. Now, because early computers were designed to process information in stages, this question became is how much information can our mind absorb or store? If you remember Ebbinghaus's forgetting curve, think about it in terms of what is the amount of information that I can hold in my brain at any at one time, and what information is being stored. So we have these two questions of memory, so the amount that I can store, and attention, my ability to prioritize different information in the environment and then assimilate that information and store it in memory. Now, what some cognitive scientists did to explore this question was to look at attention and storage. And Cherry designed this, what was called a dichotic listening task. And essentially, if you think about hearing tests that you might have experienced as a child or maybe more recently, you put headphones on and they play tones in your ears, and that's to help them test whether or not you're able to distinguish sounds at a certain decibel level. Now, what Cherry did was present, rather than just testing the decibel level at which someone can detect information, they would present messages in the left ear, so message A, and a message in message B in the right ear. And to ensure that, excuse me, sorry, and in order to ensure that attention was being paid, they shadowed one message. So one message was being played more subtly than the other. And participants, what Cherry found was that participants were only able to focus on the message that they were shadowing. So the message that they were trying to listen harder to repeat at the same time. That was the only message they were able to focus on. So it's not just a matter of our brain absorbs all of the information in our environment and then it categorizes it. We find ways to prioritize that information, and other information can get left out. Now, Broadbent is another scientist in 1958 who wanted to look at how we can represent this change, this shift in attention. And so what he was actually trying to do is create a flow diagram that would demonstrate, or at least analogize, how we focus our attention. And that essentially, in this diagram, he had a filter, and that as human beings in our cognitions, we have this ability to prioritize information. And when we prioritize specific types of information, if there's other information being presented that doesn't make it through that filter, that information is never stored in our memory in what cognitive psychologists would call working memory, which we'll talk more specifically when we talk about short-term working memory and long-term memory. And so by using this model of memory, so thinking about the brain as a computer processor, what Broadbent tried to do was represent this idea of input. So if you see here, so input in a computer moving through an input processor. So this is something that computers have to do with information. If it passes through that input processor and gets the okay, it then moves to a memory unit. So in this case, something like your hard drive. And then an arithmetic unit, so something that manipulates that information. And then you get output, so putting some sort of calculus into a computer. You have the numbers in the input, it goes through the computer, and then your output is the answer. Now, he tried to compare this to how a human brain might work, which is you have your input, which is some sort of sensation, which then travels through a filter. So our brain prioritizes information based on our previous experience and also just the way our brain functions. And then that information is categorized by a detector, so our ability to categorize things, our ability to prioritize things. It passes through the detector and is found to be salient or important, then that gets put into memory. So we then remember what we just experienced if it's something that's important for us to remember. And now these flow diagrams are very important because there's a big part of the cognitive revolution was at least in America, was creating these diagrams and these models of how our brain works, because we can't necessarily get all of the little details every time we do an experiment. So the idea is to hypothesize a model, perhaps use a computer to recreate that model, and then compare the behavior of the computer with the behavior of a human. And so that was a really important shift that was happening around this time with Broadbent. So if we supplement our timeline, we now have Skinner publishing verbal behavior challenge to that verbal behavior from Chomsky, providing an alternate perspective. And then we had Nesser, who published the first cognitive psychology book. So rather than the first psychology book or psychology degree being started by James, Nesser decided to distinguish cognitive psychology as a specific branch of psychology, along with clinical and social and a lot of these other questions that are being asked. Now, just to note, we're focusing primarily on American psychologists. Now, in Europe and Europe in general, there were still a lot of cognitive psychologists developing theories. If you've ever heard of Gestalt psychology by Max Wertheimer and Kerner, they worked a lot on this idea of perception and how our brains organize information alongside all of the behaviorists doing their experiments in America. And we'll talk more specifically about those psychologists, but in terms of American psychology, this was a big push away from behaviorism and into this realm of thinking about the mind. And that was kind of solidified with Nesser's first cognitive psychology book. Now, speaking more generally about this development of cognitive psychology, another reason why it became more popular is that we were able to start thinking about how, not only how our brains are like computers, but how we could make computers like our brains. And this led to a huge field in artificial intelligence, or some huge shifts in artificial intelligence, and this idea of creating a thinking machine. So McCarty, making a machine behave in ways that would be called intelligent if a human were so behaving. So this is artificial intelligence is a really popular topic, especially in science fiction right now. And so thinking about how we can model our brains using computers and change computers' intelligence, considering how we use our brains, is a really interesting field, and we'll talk a lot about that in terms of a lot of the computer models that are developed. Newell and Simon then came along, or during this time, they created something called the Logic Theorist Program. And what this could do is, rather than just those kind of rudimentary calculus equations, this is something that would apply logical theory to different mathematical theorems. And so kind of trying to make computers problem solve in more complex ways. And it's a really fascinating area of study, and artificial intelligence will be covered a lot more in pretty much every chapter of this book. So now we come to modern day, and that was a really rudimentary coverage of Introduction to Cognitive Psychology, but focusing primarily on that shift and the importance of using empirical data to be able to actually represent what's going on in our heads, moving from more analytic introspective methods to behaviorist methods of observable behavior, and then marrying the two and saying that, well, we're going to focus on observable behavior, but we're going to consider that the mind exists, and we're going to try and model how the mind works. So for a cognitive psychologist, you start with what is known. So what we understand about our behavior, what might be accepted about our minds. Then I ask a question: how do I think memory works? Are there alternatives to how short-term, long-term working memory work? And then I'm going to try and design an experiment, and very similar very similar to experiments like Ebbinghaus, I want to isolate mechanisms, and I want to establish what those questions that I'm asking in a very mechanistic way to be able to design an experiment. Then I can obtain and interpret results, standard scientific method, and then I can take the results of that experiment either to challenge the results, so challenge another perspective that might be espoused in psychology, or to reinforce results. Some very interesting developments in general in science recently, in the past 15 years, where there's a huge call to replicate results from studies and have open publication methods. And this is a big part of being a good scientist, is being able to use that information that you've learned from previous experiments, and then either to challenge those results and ask a question that might be in opposition to those results, or ask the question as to whether or not an effect is as powerful as what it was espoused to be. And so it's really important for scientists to be able to go back and redo experiments and recreate the questions that might have been asked previously to see if the results are still the same. So I talked kind of vaguely about this shift from behaviorism to cognitive science and this idea of models and the importance of models. And models are very important in every area of science. But in cognitive psychology, I'm going to focus specifically on two, and those are structural and process models. Now, the idea of a structural model, you've probably seen this in a lot of different circumstances, but it's a representation of the actual physical structure. Now, this is something that's used predominantly when we're actually trying to think about how the brain works. So this example right here with the four lobes of the brain, being able to talk about how the different areas of the brain work and what they're responsible for is an important use of these structural models. The brain looks vaguely similar to the example that I've given here, but it doesn't look exactly like that. It's not multicolored. It's not segmented into four different areas. But in terms of our understanding of the brain, using these structural models helps us isolate these different areas. To be able to talk about the occipital lobe in terms of sight is very useful if I can look at a representation of a brain and know, oh, the occipital lobe is right back here. Oh, so if I get hit in the back of the head, something might go wrong with my eyes. And it's a really important part of understanding the structure of how things work. The structure doesn't necessarily have to mimic the object exactly, though. This is a representation of the visual system. And you don't have to worry about knowing all of the different components, but this is kind of like a circuit map, if you've ever seen one of those in physics or any electronics courses you might have taken. The function of this is to map the visual system and how all the little parts relate to each other and are connected, focusing on the structure of that system. So each one of these little boxes is a component, and each line is a connection to another component in the visual system. And these can be as simple or as complex as the scientist who's using them in order to describe that structure wants them to be. Now, the second type of model that we focus on a lot in cognitive psychology is a process model. Now, you're still going to use representations of things in order to describe how a system is related to itself, or how the pieces of a system are related to itself. But process models focus primarily on the actual action that system undertakes. In this example, we have one process model of memory storage, and the idea that we have input, which then moves through sensory memory, which then moves through short-term memory, which then moves into and then is either output, so used, reiterated in terms of this little spirally arrow, and then is stored in long-term memory and sometimes accessed. So these arrows are much more directional, and the goal is to represent the action of the system. It's another good example of a process model, the idea of long-term memory moving into different types of memory, and you'll see this example in your book as well. But that's the important distinction as far as structural and process models are concerned, is this idea of structural models focusing on the actual composition of the object or system, and the process model focusing on how that system actually works and how information, in the case of cognitive psychology, moves through it. Okay, so that's it for chapter 2. Chapter 1. I'm so sorry, man. That's it for chapter 1, lecture 2. If you could swing over, complete the quiz. The quiz will not be due until next week. Please check the due date for that. I'm giving you a little bit more time. If you have not completed your chapter 1 notes, complete those, please. Those need to be done before we start chapter 2, and those will be a really useful tool for you. So you have until tonight at midnight to complete those. Also, start reading chapter 2. If you don't have your book yet, please let me know. We'll need to find a way to get you a book. Other than that, if you have any other questions, comments, or concerns, please let me know. And as always, have a safe and pleasant weekend.